Hello, everybody. I'm Jahan Lu from Department of Computer Science, University of Helsinki. Today, I would like to introduce our research work on category calculus and algebra for multimodal data. In this talk, I will first introduce the multimodal database. This is a new kind of database which can handle different models of the data storage. Then I will introduce how to use category theory to query a multimodal database. I will introduce categorical algebra and the calculus. Then I will define different algebraic transformation rules. Those rules can help to optimize the query on this category database. Finally, I will make the conclusion. This talk will involve more in database knowledge, and I will only use some basic knowledge on category, such as limit and the thing category. Have you heard the buzzword big data? Data come from different sources and have different formats. The big data may come from the smartphone, camera, and social media. Those data have different size of volume and have different format. One big challenge about big data is called variety. That means data have different formats. For some example of application, customer 360-degree view. In these applications, the customer data may include different sources, such as social media, gaming, entertainment, banking, finance, personal information, and purchase records. One typical task is how to integrate those different sources of the customer information and provide the 360-degree view for this customer. In these slides, we show an example of previous customer information. We have four types of data set. One is table, social network, key-value pair, and the order information of customer. In these tables, there are three columns, which include the customer ID, name, and credit limit. In the social network, we can join these four sets of data sets and find the holistic information of the customer. For examples, from the relation table of John, we can find its credit limit. And from this social network, we can know that Mary is a friend of John, and John makes some the order information about some the book and the toy. In order to make a 360-degree view of a customer, we need to integrate and join those four different types of data together. In above applications, there are four types of data: relation, graph, hierarchical, and key-value. Then one challenge from the database community is how to integrate those heterogeneous data to provide a unified service for the query and processing these four types of data together. We propose to use a multimodal database system. This system can provide a holistic engine to process different types of data together, include XML, RDF, tabular, spatial, text, JSON. One database engine can process those different types of data together. You may know a traditional database. This is a software designed to efficiently manage data, where traditional systems store data in terms of the tables. So this is called the relation DBMS. This is examples of relation database, which include one table with four columns: student ID, first name, last name, and department. they store those information in a table, so we call it a relation database. Relation database can store only data in tables, but a multimodal database, for short, MMDBMS, can support different model of data, including the document, graph, relation, and the key-value models. Those different data can be managed with a single integrated backend. In the previous examples, there are 4 types of data. Those 4 types of data can be managed by a typical MMDBMS. One multimodal database can store those 4 types of data together and provide a holistic query engine. For the advantage of MMDBMS over the traditional relation database, first, MMDBMS can handle diverse data type. Previous relation database can only support the relation table, but now the multimodal database can handle the data include graph, relation, document, and key-value data. Second, MMDBMS can provide enhanced query capability. For example, in order to provide the spatial data, MMDBMS can provide the spatial query, and to handle the tree hierarchical data, MMDBMS can provide the path navigation, and for the graph data, they can provide the subgraph pattern matching query. Third, MMDBS also can provide the flexible schema. The previous traditional RDBMS should have the fixed schema, but now the MMDBS can have the flexible schema. There are a lot of multimodal database products such as Oracle, OpenDB, DB, and MacLogic. For example, OpenDB is an open source database which can support graph, document, key-value, and object models. This is the interface of OpenDB, which organizes the data as a graph. Recall the previous 4 types of data. Let's consider a recommendation query. Return all products which are ordered by a friend of a customer whose credit limit is greater than 4,000. Based on this query, we can see that the John is a friend of the Mary, and the credit limit of Mary is 5,000, which is greater than 4,000. Then we need to return all the products which are ordered by John. So we need to access this key-value data, and then we access this order information by John. Then we need to return all the products which include toy and book are ordered by the John. Therefore, in order to answer this recommendation query, we need to integrate these 4 types of data together. Based on the previous query, we can write a query for the OpenDB. From this query, we can see that it extended the SQL query use select from where. Select expand outer nodes. This shows that the graph information, order line, and product number. This is the traverse of the JSON document. From is the customer table, and this specifies the condition of the credit limit. So based on OpenDB, we can use this query to answer the previous recommendation query. One key challenge for multimodal database is to develop a unified model and theory for multimodal data. The previous traditional relation theory is only used for the relation table, But now we have the multimodal data. Therefore, we need to develop a unified new model and theory for multimodal data. One possible solution for this theoretical foundation is to use category theory, which was introduced to mathematics world by Samuel Allenberg and Sander Maclean in 1944. Their purpose is to develop a unified language of topology and algebra. In this paper, database can be considered a set, category, object are sets, and morphisms are functions. We assume it is a thing category or postal category. Given a pair of objects x and y in category C, for any two morphisms f and g from x to y, we see C is a thing category if and only if the morphisms f and g are equal. In the example of the student and the course examples, assume that we have three different data sets, which include the relation tables, property graph, and the XML file. Those three different data sets can be unified as a category. In these examples, each object is a set which includes different values. For example, the student set includes the student ID, and which includes the first name and last name, which is two functions. In the field of relation database, relation algebra and relation calculus are developed as a two formal language for query database. Similarly, we should develop category algebra and categorical calculus. This can be developed to query the category database. Recall that in relation algebra include different operators such as selection, projection, union, intersection, difference, Cartesian product, and also the join operators. This slide shows two examples of the query tree, which include different operators. In these trees, there are two tables, teachers and course do the join. Then they will continue to join with instructor. Then the sigma shows the selection based on the department name, and finally do the projection for the name and the title attributes. Then we introduce the categorical algebra. We first define the set operators. In the unary operators, we map one set into another set. First, we define the map function f, which maps one set by the function and map to another set. Then selection sigma means that we just select a subset. Projection means that we can map one relation object R to another relation object R prime. Then R prime, it just select the columns from this original object R. Second is the binary operators, means that we combine two sets and get the third set. The first is division. We have the two sets, and we can divide A divided by B. And I will give some example to illustrate this division operators. For the get parent D1, D2, then we get some parent, which D1 is parent of D2. Then get ancestors D1, D2 also used in a tree structure. Ternary operators means that we have three different objects, then we can return another relationship object. In the operator get which STE means that we want to find all the nodes from S and all nodes from T where S is reachable to T. Get n hop means that S is n hop reachable to T. Then we introduce the category operators. First, sets and function to category. We are given some sets and the function between these sets. We can use these CT operators to generate a category use this given set, objects, and morphisms. Second is category to set, which can convert a category into a relational object. So these operators will compute the limit of this category and generate a relational object. Consider the previous example of this category, which describes information about the student course registration. Then we are given a query, find all the courses taken by Smith. In order to answer this query, we can use these two operators defined by the categorical algebra. First, we use the sigma operators. These operators can select a subset of registration. Then it shows that the registration to student and the last name equals Smith. Then we find the subset of registration for R1. In R2, we just do the map of the path. Then we from the registration to the course and to the titles. That means we can find all the courses which are taken by the Smith and find the course titles. Then in a second example, to find the title of course taken by all the students. In these examples, we use the operators division. So S1 means that for all the registration by some students, we divided by all the students. So S1 means that we can find all the registration information which are for some course which is taken by all the students. Then in S2 is just to find the course and the title. So when we return S2 means that we can find all the title of the course taken by all the students. The detailed definition about this division can be found in our paper. Recall the previous example of customer category. In this slide, we show a two query plan tree. These trees include different operators defined in previous category algebra. Based on these examples, the tree of A and B will return the same answer, but they can define different operators. Later, we will introduce some the algebraic transformation rules, which can be used to transform one query tree to another query tree with the purpose of the query optimization. Now we introduce the category calculus. Category calculus is a declarative language which is used to describe results in a category. Previously, we defined category algebra, which is a procedural language for listing operations in a category. Later on, we will define the equivalent between the category calculus and the category algebra. This table shows some example of formula in category calculus. Here, x1 belongs to O1 means that x1 is a variable. It's an element in the set of O1. And this formula f1 xy f1 is defined from x1 to x2, and x1 belong the set S1 and S2 belong to set S2. And F1 is a composed morphism for F2 and G1. Then we see this example, x1 belongs to S1 and x2 belong to S2, and x1 is reachable to x2 means that x1 is a node in a graph and x2 is also a node. Then x1 is reachable from the node x2 in the graph and x1 name equals John. So this predicate is only used for the graph data to specify the reachable condition. Then this example shows the tree data predicate. x1 belongs to D1, x2 belongs to D2, then x1 is ancestor of x2, means that in a tree, x1 node is ancestor of x2 in a tree. Here we define the unsafe variable. Unsafe variable refers a variable that has possibly infinite number of the values. It is unbounded. In this examples, x2 belongs to S2, so x2 is safe variable because it has a bound in a set of S2. However, x1 is unsafe variable because there's no constraint for the values of x1. So in these three examples, x1 is unsafe variables. In our definition of category calculus, we only use the safe variable. Recall the previous examples. One query to find all courses taken by Smith. This is the two operators based on category algebra. Then we can write the equivalent calculus shows x belong to the title and y is registration element. Then we need the y student last name is Smith and x and y's course title equals x. So that means that we can find all the course title which are taken by the last name of a student, which is Smith. In this example, we need to find the titles of course taken by all students. In previous examples, we given the two operators which defined by the division of operators. Then we can write the equivalent calculus that include x belong to the title and any y belong to the student. We should there exists a R which is registration R student title course title equals x. That means that we find the title of course which should be taken by all the students. Next, I will define some algebraic transformation rules. Based on these rules, we can perform the query optimizations. In the following, I will show some the algebraic rewriting rules. The purpose of these rules means that we should the equivalent of the two expressions of the category algebra. Then, in order to answer one practical query, we can rewrite based on these equivalent rules. The purpose of this transformation of rewriting is to improve the performance of these queries. In this slide, we can show some formula based on the limit and the projection. So the first formula shows that if we first generate a category and compute the limit, then we do the projection, then which will be equals to original object of S1. Secondly, then this shows that we can push the sigma, which is selection operation, to one or multi objects in the limit. So in these examples, if we first compute the limit of the two sets, then perform a selection which will be equals that we first do a selection and compute the limit. Because we first computed the limit, the selection means that we can reduce the size of this S1 and reduce the cost for compute the limit operator. The first formula shows that we can push sigma to one or two multi-objects in get reachable. Get-reachable means that in graph data, we want to find the two nodes from S and one another node to T, and S is reachable to T. So the first formula shows that we can first do a selection, then compute the get-reachable, which will be cheaper in most cases. The second formula shows that if we want to do a Cartesian product between the two sets, Fs1 and Gs2, then we can first compute the Cartesian product and do the product for these two functions, which also equivalent. The third formula shows that we can commuting pi projection operation with the limit operations. So we first do the projection, then we compute the limit. In this slide, we show that we can commute some function g with the limit operations. Assume that this diagram holds, means that if we have some function from S1 to S2 through the function f1, and S2 to prime, S2 prime through the G2, if f1, G2 is equivalent to the G1 and f2, then we can change the orders of the function g and the limit operations. Then in this example, I show the two query plan which are equivalent. Based on the previous transformation rules, we can rewrite the query plan 1 become the query plan 2. You can see that we can change the order of the limit and switch with the selection operations. In this way, we can improve the query performance. Therefore, the previous defined rewriting algebraic rules based on the multimodal data can be used for the query optimization of multimodal database. Now I introduce the expressibility power of previous category algebra and categorical calculus. Category calculus and category algebra can express of all the following queries, which include the relation calculus and the relation algebra queries. Also include the graph pattern matching and graph reachability queries because we define the reachability predicates. Finally, this also can be used to define the XML trig pattern matching queries because we have the ancestor and its parent child relationships. For the time and the space complexity of the category calculus and algebra, we have the following results. Consider category C with P object and Q morphism. Let the maximum number of elements in any object of the C be n, then the data time complexity of computation for category calculus and algebra is bounded by Q times n power to P. This still is polynomial time to Q and P. The space complexity of this computation is handled by ns space log n, so the space is also efficient. Finally, I introduce some of the previous work. There are a lot of previous work which apply the category theory on relation database, but this paper we focus on the multimodal database. Some previous paper on category theory for relation database, such as in the 1997, Lipkin and Wang showcased the connection between database operations and the categorical notion of the monad, and also the Schultz and Spivak also introduced a categorical query language that serve as data integration scripting languages. On the other hand, there are also existing algebra and calculus for the relation data. graph data and object-oriented data, but these papers focus on define the algebra and the calculus for the multimodal data. Finally, I summarize the main contribution of this paper. In this paper, we develop a multimodal database as a thin set category, and we define the category algebra and the category calculus and prove their equivalence. And we also develop algebraic transformation rules for query optimization of the multimodal database. In this paper, applied category theory can contribute to the practical query processing and optimization of multimodal database system because we define the algebraic writing rules. These rules can identify equivalent transformation rules for the algebra and can be used to optimize the query processing. The final slide shows some selected reference. Thank you for your attention.